Finding the shortest path. The next problem we consider is one that everyone with a driver's license has faced before. Given a starting point S and an endpoint T and a network of one-way streets, find the shortest path from S to T. We will present an algorithm that will find not simply the shortest path to T, but the shortest path to any point on the map. The algorithm is called the Diestro Algorithm after its inventor, the Dutch mathematician Diestro W. Diestro. Our input is a directed simple graph G. The edge of G all have a positive cost. The cost of EI will be denoted by D of EI. One can think of a D of EI as the length of EI. While looking for the shortest path from S to any given vertex T, we will associate a number delta of Vi to each vertex Vi. This number can be thought of as the length of the shortest discovered path from S to Vi. Originally, we set delta of S equals to 0 and delta of T equals to infinity for all T not equals to S, since we have not yet discovered any paths from S to T. In what follows, we split the vertex set V of G into two parts, the set S vertices to which we already have a path from S, and the set T of vertices to which we do not yet have a path. So at the beginning, S is equals to the singleton S, the set of singleton S, and T is equals to V of G minus such a singleton. For all edges S, V, set delta of V equals to D of SV, replacing the original delta of T equals to infinity. This makes perfect sense since it expresses the fact that if there is an edge from S to T, then the minimal distance from S to T is the length of that edge. Now we describe a generic step of the algorithm. This step will be applied several times following the initial step described in the previous paragraph. Find a vertex V in T for which delta of V is minimal. Put V into S and proceed with all the edges leaving V and go into a vertex outside S as you proceeded with the edges leaving S. More precisely, if VR is an edge with R in T and delta of V plus D of VR is greater than or equals to delta of R, then do nothing. Otherwise, replace delta of R by delta of V plus D of VR, corresponding to the fact that we have just found a shorter path to R, namely the path that consists of a shortest path to V and the edge VR. This step is often described by saying that we relaxed the edge VR. When this is done, iterate this procedure. That is, find the vertex V' in T for which delta of V' is minimal and start over. Stop when all vertices are in S, and therefore all edges are relaxed. Or when there are no edges going from S to T, the latter can happen when G is not strongly connected. Throughout the algorithm, ties can be broken in any way. An example is shown below. Example 17.15. For the graph shown in figure 17.2, Diestro's algorithm works as follows. 1. Start with the graph shown and set S equals to singleton S. 2. Relax the edges leaving S. Set delta of A equals to 4 and delta of B equals to 5. Put A in S. 3. Relax the edges leaving A. Set delta of C equals to 8 and delta F equals to 9. Put B in S. 4. Relax the edges leaving B. Set delta D equals to 10 and delta of F equals to 7. So delta of F is being reset. Originally, delta F is equals to 9 because it goes from A, but right now delta of F goes from B to f, so it becomes delta of f is equals to 7. 5. Relax the ages leaving f, set delta of g equals to 12 and delta of I equals to 16, put c in S. 6. Relax the only age leaving c, set delta of e equals to 12, put d in S. 7. Relax the only age leaving d. This happens to have no effect since delta of g is equal to 12, put g in S. 8. Relax the only age leaving g, set delta of h equals to 17, put h in S. 9. Relax the only age leaving h. This has no effect, put I in S. 10. End. Figure 17.3 shows the graph of figure 17.2 with the values of delta written next to the vertices in italics and the weights of the age written on the ages in Roman font. So figure 17.3 is the output of the Diestro algorithm. Several questions are in order. First, how do we read of a shortest path from S to some t from the output of this algorithm? We say a shortest path, not the shortest path, since there could be times when there are several paths of minimum length. Second, why is it that the final value of delta of t is indeed the length of a shortest path from S to t? Third, how many steps does it take to run this algorithm? We answer the first two questions at once by the following theorem. Before we announce the theorem, we need one more notion. Let us say that for a given vertex t, every time an edge vt is relaxed, and the value of delta of t decreases, we set pref of t equals to v. This expresses the fact that at that point there is a shortest path from S to t that ends in the edge vt. Note that pref of t is always a vertex that got placed into S before t, and that when the Diestro algorithm is finished, pref of t is defined for all t not equals to S. Therefore, as g is finite for all vertices t not equals to S, there exists a positive integer k, so that pref to the k of t is equals to S. Here, pref to the k simply means k successive applications of pref. Theorem 17.16. For any simple graph G and for any pair of distinct vertices S and T, the Diestro algorithm will either produce a shortest path from S to T and compute its length, or show that there is no path from S to T as follows. A. Once the algorithm is finished, the path whose edges listed from the end are pref of T and T, such a tuple, or pref of T and pref of T, and so on. So the final one is S and pref to the kth of T is the shortest path from S to T. If a pref of T is not defined, then there is no path from S to T. B. Furthermore, the length of any shortest path from S to T is equal to the value of delta of T when the algorithm is finished. If there's no path from S to T, then this value will be infinity. Proof. We first prove part B. In fact, we prove the following even stronger statement. We claim that at each stage of the Diestro algorithm, 1. If t is in S, then delta of t is the length of a shortest path from S to t. 2. If t is not in S, then delta of t is the length of a shortest path from S to t whose last edge is an edge from S to t. We prove these claims by induction on the size of S. If the size of S is equals to 1, that is S equals to just such a singleton as the source, then 1 holds since delta of S is equals to 0. Remember that the 1 says If t is in S, then delta of t is the length of a shortest path from S to t. So from S to S, delta of S is equals to 0. Claim 2 holds, since if st is an h, then delta of t is equals to d of st is the length of a shortest path from st with the desired property, and if st is not an h, then delta of t is equals to infinity. Now let us assume that the claims hold for the case of the size of S equals to k, and prove them for the case of S prime. The size of S prime equals to k plus 1. Let S prime equals to S union x. That is, x is the new vertex added to S in this step of the Diestro algorithm. We first show that 1 holds for x. Before this step, x was outside S. So by the induction hypothesis, delta of x was the length of a shortest Sx path Q, whose last h was from S to x. Note that every path P from S to x has to first leave S and then arrive at x. If the first vertex of P outside S is some y not equals to x, then P is not a shortest Sx path. See figure 17.4 for an illustration. Indeed, the part of P that is between S and Y cannot be shorter than Q, since if it were, then Y, not X, would be selected to be added to S in this step. Recall that by the induction hypothesis, we know that delta of X is minima for X not equals to S, and that delta of X is the length of a shortest Sx path ending in an h from S to x. We would then have to get from y to x, which would make P longer than Q. Also note that adding x to S will not change the label of the vertices that are already in S, since, by the definition of the Diestro algorithm, addresses within S are not being relaxed. Therefore, 1 is proved. In order to prove 2, let h, which is in V of g minus S prime. Note that if there is a shortest SH path ending in an S prime HH that does not end in an XHH, then the placement of x into S prime did not change anything. So our claim holds by the induction hypothesis. If all the shortest path SH passes ending in an S prime HH to end in an XHH, then the Diestro algorithm sets delta of H equals to delta of X plus d of XH, and our claim is proved, since in all such paths, the path from S to X must be a shortest path from S to X, and so have length delta of X. This proves part B of the theorem. Part A is now not difficult to see. Indeed, now that we know that the Diestro algorithm correctly computes the minimal distances to all vertices, we see that part A simply describes how we can keep track of the way those minimal distances are actually achieved. A minimal distance is achieved by a shortest path, and the path described in part A is a path achieving the minimal distance from S to T, therefore it is a shortest path. Note that the Diestro algorithm takes big O of n squared steps. Indeed, in each stage, we add one vertex to S, so there are at most n stages, and in each of those stages, we must find the vertex V, which is not in S, for which delta of V is minimal. This can be done in big O of n steps, as you are asked to prove in supplementary exercise 12, proving our claim. The Diestro algorithm has several refinements and enhanced versions. Perhaps the most widely used special case is breadth-first search. This is the special case when all addresses have weight 1, and the task is reduced to finding the path from S to T that contains the minimum number of addresses. The name breadth first search refers to the fact that the algorithm will first reach all the neighbors of S before going deeper into the graph. This is in contrast to another approach, depth first search, which we defined in exercise 8. Notes: a very readable introduction to the topics of this chapter, and the next one is Herb Wells' book, Algorithms and Complexity. A classic comprehensive textbook on algorithms is Introduction to Algorithms by Corman et al. In this book, the reader will find several sorting algorithms which are roughly as effective as merge sort, as well as a detailed analysis of the two graph traversal algorithms that we mentioned here, breadth first search and depth first search.